In this video, we are going to discuss about the common train amplifier. On the completion of this common train amplifier, the students will be able to find out the ideal maximum voltage gain for common train amplifier. In this common train amplifier, you can see the circuit. There is input which we are applying between the gate as well as the source, and this output we are taking between the source and the rail. So you can see it in the circuit diagram itself. That is the input side you can see the gate and the source, and the output side you can see the source and the drain. So since this one is a common drain amplifier, we are grounding at this drain terminal. So if drain is grounded means then source will be taking as an output. So you can see the output in the source region. Then in this circuit you can see the source voltages Vs is equal to Vg plus Vgs. So whenever we are applying the signal to this JFET gate through, that is C1, this gate voltage varies with the signal. So when there is a gate source variation, that is fairly constant, and when this gate source is equal to, that is Vg plus Vgs, we can write that Vs varies, that is source voltage varies with input voltage. And you can see the common train amplifier diagram. So this one is the common train amplifier diagram, that is we are drawing the hybrid model for this circuit. So you can see that is Vi, Rg, and this terminal, that is Gm into Vgs. Since this source we are considering as an output, so you are taking from this one, that is we will be considering this Rs term, and this will be considered in the output region. So here also we will be calculating the input impedance, output impedance, voltage gain, and the current gain. So first we are calculating the input impedance. So when we are calculating the input impedance, here this values, that is we are taking this Rs to the output side. Since the source terminal is in the output side, we are considering this Rs to the output side. So we get this equation as, and this current direction will changes from upward direction. So Gm into Vgs, Rd, Rs, V0. Now we are going to apply the terminal, that is input impedance Zi is equal to Rg, and the output impedance we know that is Z0 is equal to Z0 dash, as well as it is parallel to Rs. So we are considering that Z0 dash term as V0 divided by Id whenever this input voltage is equal to 0. So here we apply the KVL to the outer loop, so we get that Vi plus Vgs minus V0 equal to 0. When Vi is equal to 0 and Vgs is equal to V0, looking at this figure we can find out that is Gm into Vgs is equal to Id, but Vgs is equal to V0. So Gm into V0 equal to Id, and Z0 is equal to V0 divided by Id, which is nothing but 1 by Gm. So Z0 is equal to 1 divided by Gm parallel to Rs. And from this we are calculating the voltage gain. So we find out the voltage gain, I is equal to output voltage divided by the input voltage. So from that figure we can analyze that is V0 is nothing but the minus Id, that is according to Ohm's law we know that V is equal to I into R. So we are considering the output voltage. So V0 is equal to minus Id into Rd parallel Rs. Id is nothing but Gm into Vgs. You can write this equation Id in terms of Gm into Vgs. So substitute this value in this above equation, you get that V0 is equal to minus Gm into Vgs of Rd parallel of Rs, and Vi is equal to minus Vgs plus V0, which is equal to minus Vgs plus minus Gm into Vgs of Rd parallel Rs. Now you substitute the values in the voltage gain, that is Av is equal to minus Gm into Vgs Rd parallel Rs divided by minus Vgs of 1 plus Gm into Rd parallel Rs. You can cancel the term, that is Vgs and Vgs, so we will be getting that Gm into Rd parallel Rs divided by 1 plus Gm into Rd parallel Rs. So in case if this Rd drain resistance is greater than the source resistance, then you can neglect the term, so that you will be getting Av is equal to Gm into Rs divided by 1 plus Gm into Rs. If this Gm into Rs is very greater than 1, then Av is equal to 1, but it is always less than 1. So exact thing you can see, that is Zi, exact thing you will be getting is Rg, and if Rd is greater than Rd also, that is Rg. Our output impedance is exact is 1 by Gm parallel. The same thing is for Rd greater than Rd. Then voltage gain exact thing is Gm of Rd parallel Rs divided by 1 plus Gm into Rd parallel Rs. In case if Rd is very greater than Rd, then you are neglecting this term, so you will be getting Gm into Rs divided by 1 plus Gm into Rs. Thank you.